All right, here we are with step 2 of our algebraic review. The topic today is radical simplification. This is something you'll have to do in homework assignments for me. This is something you also have to do on the myriad as well. And I find that students sometimes don't quite get what I mean when I say that I want radical expressions fully simplified. So that's the task. Let's talk about what that means. All right, so first of all, let's make sure that you understand a certain definition. Perfect square, you probably do, but here's the definition. A perfect square is the square of an integer. So then, of course, 0 is a perfect square, since 0 is 0 squared. And all the other perfect squares are positive because other than 0, when we square an integer, we, of course, get a positive. This means that the sequence of perfect squares begins 0, and then 1, and then 4, and then 9, and 16, which is, of course, the square of both 4 and -4, and so on. Now, let's talk a little bit about roots of non-perfect squares. This is a place where I think that sometimes students have mistaken ideas. The square root of an integer that is not a perfect square is always irrational. I will not attempt to prove this to you. We did in semester 1 prove this for one specific instance of an integer that is not a perfect square, that is 2. We proved that the square root of 2 is irrational. Now I'll just simply say to you that if the number whose square root you take is not a perfect square, the result is irrational. Now, this has two important consequences for us. To say that the square root of a non-perfect square, of an integer that isn't a perfect square, is irrational means that it cannot be expressed as a ratio of integers, so don't do that. For instance, there are no two integers such that their ratio equals the square root of 2, and don't pretend that it is. Moreover, and this is perhaps more important, the decimal expansion of the square root of a non-perfect square neither terminates nor repeats. So that means that if you wish to give me an exact result, and that's typically what I want, then you cannot use the decimal point. So let's say that you're at work on a problem, like you will be on the homework or on the myriad, and you get to a final answer, which is the square root of 2, and that will actually happen. You'll end up with an answer that's simply the square root of 2. I want you to stop right there. I don't want you to go to your calculator. I don't want you to type in the square root of 2. I don't want you to give me a decimal point with some digits after it, because anything that you might give me, no matter how many digits it is, will simply be an approximation. Even if you write out every digit that's in the display, that's still an approximation, and I don't want that. Even if you go to an online tool like Wolfram Alpha and give me hundreds or even, I think, potentially thousands of digits, that still will be an approximation. So what I want then is an expression that contains the radical. And then what we must discuss is how we simplify expressions like that, and they are certainly simplifiable in some cases. Well, here's what I want out of you when I say that I want you to simplify a radical expression. Well, first of all, I don't want any expression under a radical to contain a perfect square factor other than 1. We must remove those. Those will come out from under the radical. Second, I don't want you to have a product of radicals, so I don't want like one radical times another radical. And then finally, I don't want division within a radical, under a radical, and I don't want a radical in a denominator. Now, what we're about to do is look at examples of all of these where you can simplify and so not violate any of these three rules about simplified radicals. So let's consider first the square root of 12. That's certainly, of course, an irrational because 12 is not a perfect square, but that doesn't mean that it cannot be simplified. It can be simplified, and I expect that it would be. For instance, if this were a myriad problem and you were to simply tell me that the answer is the square root of 12, I would immediately give it back to you, and I would probably write a little note in the margins that says, this is not simplified. I want fully simplified answers. Well, how do we simplify it? Well, we'll use that property that we proved last time, the property that says that the square root of x times y is the square root of x times the square root of y. And the way that we will use it is this, is we will write 12 such that it's a product of factors such that at least one of them is a perfect square, and then we will use that property. Okay, let me show you how this will actually work in this case. So here we go. I will start with the square root of 12. And what we wish to do is to write this as a product of factors, at least one of which is a perfect square. And I suppose the way to do that is obvious. We'll write that as 4 times 3. Of course, it's perfectly true that 12 is also, say, 2 times 6, but that doesn't help us at all because neither 2 nor 6 is a perfect square. Now, at this point, we will use that property that the square root of x times y is the square root of x times the square root of y. And we will write then the square root of 4 times the square root of 3. And the square root of 4 is, of course, simply 2. So we end up with 2 times the square root of 3. And that is our fully simplified answer, because 3 does not have any perfect square factors, of course, other than 1. And if we were to pull that out, that wouldn't help at all. So that's our final answer, 2 times the square root of 3. Let's do another, 3 times the square root of 400. And I'll actually show you that this can be done in various ways, some shorter, some faster. So here, 3 times the square root of 400. And it might occur to you that 400 does have the perfect square factor of 100. So we could write this as 3 times the square root of 100 times 4. Now, once again, there are other ways to factor 400, but this one is useful to us because we found a perfect square factor. So this then becomes, by that property we've used before, it becomes 3 times the square root of 100 times the square root of 4. And then notice what's happened. The square root of 100 becomes simply 10. Oh, yeah, and look, I didn't even notice this at first. Our other factor is also a perfect square, so that becomes simply 2. So it becomes 3 times 10 times 2. And actually, in this case, there are no radicals left at all. Now, there might have been, of course, but in this case, there are not. Now, there's another way to do this. You might have simply noticed that 400 is itself a perfect square. When we look back over the work we did before, this should really come as no surprise because 400 was factored as 100 times 4, and the product of perfect squares is always itself a perfect square. So then, of course, 400 is a perfect square, so we simply could have written this as 3 times 20. 20 squared is 400, and then, once again, the final result of simplification would be 60. All right, now, let's look at type 2 type simplification, where we have a product of radicals. In this case, the root of 24 times the root of 6. Now, there are two strategies that you could pursue, two ways that you could go about this. You could start with the property that the square root of x times the square root of y is the square root of xy, and then do some type 1 simplification work, that is where we look for perfect square factors. Or you could type 1 simplify both root 24 and root 6, that is, look for perfect square factors in each, and then use root x times root y equals root xy. So let's do this in both ways. I'll do one on the left, one on the right. So let's see, root 24 times root 6. We can simply collapse this immediately into one radical, and that will be 24 times 6, which will be, let's see, what will that be? That will be 120 plus 24 more, so that will be 144. So then we end up simply with 12. Oh, that turned out to be really very nice. Now let me show you the other way. Root 24 times root 6. Now, which of these two strategies will be simpler in a particular case? Well, it can be hard to know. You can pursue either one. So the other strategy would be root 24 times root 6. And then let's look for perfect square factors in each of the two that we find there. Okay, well, let's see. 24, perfect square factor. Ooh, there's a 4 in there, right? So we can write that as root 4 times 6, and then we've still got the second root 6. And the root 4 times 6 becomes root 4 times root 6, and we still have that second root 6. And then root 4 is, of course, 2, followed by root 6 by root 6. And then, of course, just simply by the definition of root 6 times root 6 has to be 6. So we end up with 2 times 6, which is 12. So the last two, we didn't end up with any radical expression. Sometimes that happens, sometimes that does not. In this case, and the prior one, it did not. All right, so let's look at an example of type 3 simplification. The square root of 12 over 25. The reason that we say that this is not simplified is that it contains division under a radical. In any such case, we're not done. We have to simplify. And here to simplify, we'll make use of the property that the square root of x over y is the square root of x over the square root of y. We didn't prove this together in the previous PowerPoint, but I did have you do it on the homework assignment, so this is something that we now know. Okay, so here we go. So we have the square root of 12 over 25. Apply that property. That becomes the square root of 12 over the square root of 25. And then as for what we do with this, well, we know how to simplify such expressions as this, of course. The bottom, the square root of 25 is simply 5. That's very nice. And then the square root of 12. Well, we've seen that before, right? 12 is 4 times 3. So the square root of 12 becomes the square root of 4 times the square root of 3. And the square root of 4 is 2. So this ends up as 2 root 3 over 5. And that is the final simplified form, okay? We don't violate any of our rules. 3 doesn't have a perfect square factor. We don't have division within a radical, and we don't have a radical in the denominator. And also, we don't have a product of radicals. So that's fully simplified form. All right, so let's do another one, root 45 over 28. Now, there are potentially different ways to start something like this. One could look at 45 over 28 and ask oneself whether that simplifies. I don't think that it does. 28 has factors of 2, 2, and 7. 45 has factors of 3, 3, and 5. So I don't think any simplification is possible initially of the fraction 45 over 28, but sometimes it would be, and you might want to do that to begin. Though if you don't, I mean, no harm done ultimately. Okay, so we'll apply that that property that I mentioned before. Root 45 over 28 becomes root 45 over root 28. And then we simplify that. Okay, so root 45, look for perfect square factors of that. Well, that can be written as 9 times 5. And as for root 28, ooh, I see. That's root 4 times 7. And again, the reason we do it like this is we wish to have a perfect square factor, so we can rewrite it as the square root of a perfect square times another radical. So that becomes root 9 times root 5 on the top. On the bottom, it becomes root 4 times root 7. Oops, root 7. So let me fix that. Of course, that's multiplication. You don't have to put the multiplication symbol in. Sometimes it seems clearer, though. It's up to you. Now, root 9 on the top is, of course, 3. So we have 3 root 5 on the top. Then on the bottom, we have the square root of 4, which is 2, and then root 7. And you might think that you would be done. You've certainly done some simplification work, but if you look back at my definition of simplified form for radical expressions, you will realize that this is not fully simplified, and the reason is that we have a radical in a denominator. Okay, so we have to take care of that. And the sort of trick here, honestly, it does seem a bit like a trick, but it works for sure, is to multiply both top and bottom by that radical expression that occurs on the bottom. Okay, so that's a root 7. So what we'll do is we'll multiply both top and bottom by root 7. And of course, notice that we haven't changed this value in any way, because what we really did is multiply by root 7 over root 7, which is just 1. And when you multiply by 1, you don't change your quantity, of course. You just, in this case, change the way in which it's expressed. So on the top, let's see. Now, I'll write this with a single fraction bar initially. Perhaps that will help. So that'll be 3 root 5, root 7. And then on the bottom, it will be 2 root 7, root 7. And then, well, the bottom's easy, right? Root 7 times root 7 is simply 7. So we have 2 times 7, which is 14. And on the top doesn't count as simplified because we have a radical expression times a radical expression, and we don't end there. What we do with that is we rewrite it as the square root of 5 times 7, which is 35. And notice that that root 35 contains no perfect square factors. The only non-trivial factorization here is 1 times 35. The only non-trivial factorization is 5 times 7, and neither 5 nor 7 is a perfect square, so root 35 cannot be simplified. And then we finally end up with 3 root 35 over 14, which is fully simplified form in this case. That's how I would expect to see this. And again, let me just reiterate the point on a test, on a homework assignment, on the myriad. If you were to leave it at some prior stage, like for instance, if you were to leave it as 3 root 5 over 2 root 7, that doesn't count as fully simplified. If it's a myriad, I simply hand it back to you. If it's another kind of assignment like a test, I'll take a point off for that. Okay, so let's now look at 1 over 2 minus root 3. This doesn't count as fully simplified because we have a radical in the denominator. So we have to get that radical out. And there is another kind of trick here. Notice that on the bottom, we have what mathematicians would call terms instead of factors. You have terms when you add or subtract. So we have the term 2 and we have the term negative 3 on the bottom. And the way that you handle that when you have a radical as a term is you multiply both top and bottom by the conjugate of the bottom. And what I mean by conjugate is this, is you simply, well, you have either addition or subtraction of two terms and you flip the sign. So the conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. So here we go. Let us multiply both top and bottom by the conjugate of 2 minus root 3, which is 2 plus root 3. And you might wonder, well, why do that? Well, first of all, you should realize that we can do this if we want, right? Because of course, 2 plus root 3 over 2 plus root 3 is 1. So we've just multiplied by 1. So we haven't changed our quantity. We have just changed perhaps the way in which we will express it. So of course you can do it. And as for why you would want to, well, watch what happens. Okay, so on the top, we simply have 1 times 2 plus root 3. So I'll simply write that. And on the bottom, I'll go ahead and write as an intermediate step 2 minus root 3 times 2 plus root 3. And all of that is on the bottom. I tell you what, I'll rewrite this so it looks a bit better. All of that is on the bottom. So let us have a longer fraction bar. So here we go. 2 minus the square root of 3 times 2 plus the square root of 3. And let's multiply out the bottom. This is something that you were certainly taught to do in Algebra 1 class. This is a so-called binomial times a binomial. We have the two terms 2 and negative root 3, and we have the two terms 2 and positive root 3. So two terms times two terms, which is a binomial times a binomial. And you were taught to do this in some way or another. Perhaps you were taught the FOIL method, first, outer, inner, last. That's not the way that I actually prefer to do these. I think the better way to think about it is this, is you take the first term inside the first set of parentheses and multiply it by each term in the second. And then you do it again with the second term in the first set of parentheses. You multiply it by each term in the second. So we have a 2 times a 2. Perhaps I'll draw arrows to make this clear. We have a 2 times a 2, which is a 4. And then we have a 2 times a positive root 3, which is a 2 root 3. Let me extend my fraction bar so we'll have enough room for all of this. And then we do the same thing with the negative root 3. The negative root 3 multiplies by the 2. So we have negative 2 root 3, and perhaps you notice something cool that's about to happen. And then we have the negative root 3 times the positive root 3. Well, let's think about what that is. Negative times a positive is a negative, so we know that it's a negative. And then it's a root 3 times a root 3, which is, of course, 3. And then let's think about what the bottom becomes. Well, first, of course, we have 2 plus root 3 on the top. And on the bottom, well, let's see, we have a 2 root 3 minus 2 root 3. That's 0. Notice that the radical expression is now gone. See what happened then when we multiplied by the conjugate? We removed the radical from the bottom and as it were shifted it to the top. And then after that, we have a 4 minus 3, which is simply a 1. So I'll write that as a 1. And then I wouldn't complain, honestly, if you left it as 2 plus root 3 over 1. That does count as fully simplified. However, of course, we can simply write that as 2 plus root 3, which is really very cool, isn't it? 1 over 2 minus root 3 is equal to 2 plus root 3. And that's our simplified form. Oh, side note here. The reason why we in general wish and why I require you to simplify radical expressions in this way is that once simplified, they become so much easier to work with. 1 over 2 minus root 3 is relatively difficult to combine with other expressions, especially ones that contain radicals. 2 plus root 3 is much easier to work with. So that's why we do this kind of work. Okay, so here's another one, 2 minus root 5 over root 2 plus root 5. And then we're going to do the same kind of work we did before. So 2 minus root 5. Notice that we have terms on the bottom that contain radicals. So the strategy, once again, is to multiply top and bottom by the conjugate of what's on the bottom. So the conjugate is simply when you flip the sign between the two terms. So the conjugate will be root 2 minus root 5. So that's what we multiply by on both top and bottom. So root 2 minus root 5. And I tell you what, I'll write this with a single fraction bar. It might help us to see what's about to happen. So we have on the top 2 minus root 5 times root 2 minus root 5. And on the bottom we have root 2 plus root 5 times root 2 minus root 5. And then let's do the work on both top and bottom. I know it's a little tedious, but there's no way around it really. probably need a longer fraction bar. There we go. So on the top, we have, first of all, the 2 times the root 2, which is 2 root 2. And then we have a 2 times the negative root 5, which is negative 2 root 5. And then we switch to the root 5. Okay, so we have a negative root 5 times the root 2. A negative times a positive is negative, of course. And then I'll go ahead and write root 5 times root 2 is root 10. So we have minus root 10. And then, even more fraction bar we need. And then finally, we have negative root 5. Oh, no, let me make sure that I've done this right. So 2, oh, no, I'm going to start over. Sorry. I did it in an order different than the order that I told you to do it before. So let me make sure that I'm consistent about this. So I'll start over. Sorry. Okay, so long fraction bar. So I have a 2 times root 2. And then I have the 2 times the negative root 5, which is negative 2 root 5. And then I switch over to the negative root 5. So I have negative root 5 times root 2, which is, like I said a moment ago, negative root 10. And then I have negative root 5 times negative root 5. That's a positive, of course. And then root 5 times root 5 is simply 5. So we have 5. And then on the bottom, well, let's think about this. Initially, I have root 2 times root 2, which is 2. And then I have the root 2 times the negative root 5, which is negative root 10. And then let me switch over to the negative root 5. So I have switch over to the positive root 5 in the left expression. So I have root 5 times root 2, which is root 10. And you see what's about to happen there, don't you? And then finally, I have positive root 5 times negative root 5, which is, of course, a negative, and root 5 times root 5 is 5, so that's simply minus 5. And then, okay, so let's see what we're going to get. On the bottom, I have negative root 10 plus root 10, which is 0, and then I have 2 minus 5, which is negative 3, so that's all that remains on the bottom. So, job well done. We don't have any more radicals on the bottom. And then as for what's on the top, I have a 2 root 2 minus a 2 root 5 minus root 10 plus 5. Okay, so there's some complexity in the top for sure, but this does count as simplified form because we've removed the radical from the bottom. And if you look at the top, it might occur to you that you can do something with that, but honestly, you cannot. Root 2 is fully simplified, root 5 is fully simplified, root 10 is fully simplified, and so none of the terms on the top can be combined in any way. Only if the radicals were the same could they possibly be combined. Okay, so that's fully simplified form. And then let's do this beast, okay? Just to make sure that we can do all of this, this is our final example. So we have 12 root 18 root 24 over root 2 plus root 3. Okay, now there are various ways that you can go about this. What I think I will do is this. I think I will work on the top and leave the bottom alone initially, and then I will worry about the bottom. Okay, so allow me to do this. I'm simply going to work on the top initially, and I'm not even going to include the bottom. Okay, so now as for how I wish to do this, we could combine that into a single radical when we multiply 18 by 24, but that results in a relatively large number that we would then have to factor. I think it's easier to simplify root 18 and root 24 and then see what we've got. Okay, so is there a perfect square factor in 18? Yep, 9. So we'll write that as 9 times 2. And then is there a perfect square factor in 24? Yep, 4. So we'll write that as 4 times 6. And then let's see, we have the 12. The root 9 comes out as a 3, and this is all multiplication, of course. And then we have a root 2. And then the 4 under the radical comes out as root 4, which is simply, I'll just skip a step here and call that 2. Oops, I called that 4 times 16, didn't I? Don't know why. So I need to erase that. Oh, it won't allow me to erase. So I tell you what, I'll simply cross through it then. The technology is not perfect, of course. So that was 6. So I had a root 4 times a root 6, and root 4 is 2, so I have 2 root 6. And then let's see, what does this become? I have a factor of 12 and 3 and 2. So that becomes 36 times 2, which is 72. Yep, that's right. And then let's see, what else do I have? I have a root 2 times a root 6, which becomes a root 12. And then at this point, there might well be simplification work that we can do because we brought the 2 and the 6, which were under radicals, into a single radical, and sure enough, 12 now has a factor, a perfect square factor, so we'll have to work on that. So we'll write the 12 as 4 times 3, and then that square root of 4 will come out, which is 2, and then we have the 2 times 72, which is 144, so 144 root 3. So that's the top, okay? That's the top. Now let's take that into the original expression. So 144 root 3 over root 2 plus root 3. And then what are we going to do? Well, we have terms on the bottom, at least one of which contains the radical. That means we multiply top and bottom by the conjugate of the bottom, which is root 2 minus root 3, root 2 minus root 3, which again means, of course, we just multiplied by 1. So all we're about to do is not to change the value of this expression, but just simply the manner in which it's expressed. And then let's do our work, okay? So let's see, on the bottom I have root 2 plus root 3 times root 2 minus root 3. So initially root 2 times root 2 is 2. And then root 2 times negative root 3 is negative root 6. And then let me switch over to the positive root 3. So positive root 3 times positive root 2 is positive root 6. And then I have positive root 3 times negative root 3, which is just simply negative 3. And then as for the top, well, let's see. This is going to be kind of interesting, isn't it? I have 144 root 3 times root 2 minus root 3. That's distribution. The 144 root 3 must be distributed over root 2 minus root 3. So 144 root 3 times root 2 will be 144 root 6. And then I have 144 root 3 times root 3. Well, the root 3 times root 3 is 3. So that's 144 times 3. Okay, and then let's see what we've got. On the bottom, the negative root 6, positive root 6 becomes 0. And then we have 2 minus 3, which is negative 1. And then on the top, we have 144 root 6 minus, well, let's see, 3 times 144. Let's see, what will that be? I tell you what, I'm going to go to a calculator and type that in just to make sure that I can get this right. Give me just a second here. If my mental math skills were stronger, I wouldn't have to do this, but I do. So that is 432. And actually, I'm going to carry this through until the very end because there's a way in which this can be simplified. It doesn't involve anything to do with radicals, but other work that you're supposed to know how to do. Okay, so we have the top 140 for root 6 minus 432 over negative 1. Now, when we divide by negative 1, that means that we change the sign of each term in the top. So this turns into 432 minus 144 root 6. And then we're done, okay? And then we're done. Now, it would be possible, I think, to factor something out of both 432 and 144, at least to 2, of course, because they're both even, but that is not necessary, and then that finally counts as our fully simplified form. And just compare this to the original expression. The numbers are a bit bigger, of course, but it is a much easier expression to work with than the original one. So there it is. That's radical simplification, and this is something that you will be expected to do all semester long.